we are going to show you how to use the chi-square test for independence of two factors, which means that we are going to be dealing with categorical data. So let's consider the following example. We had a survey with 200 participants where each of them was asked two questions with a possible answer yes or no. The first question was if they had a dog or not, and the second question was if they were going for regular evening walks. The answers were summarized in the table that you see now on the screen. So as you see, 110 participants answered that they were going for an evening walk regularly, of which 70 said they had a dog and 40 that they didn't. Now 90 participants said that they were not going for an evening walk usually, and 25 of them had a dog and 65 did not. Now you see the sum of the first column is equal to 95, which is how many people had dogs, and the sum of the second column is 105, which is how many people didn't have a dog. And the sum of the first line is 110, which is how many people were going for evening walks in total, and sum of the second row is 90, which is the number of people which were not going for evening walks. Now when you observe the table, you see that most of the people who had dogs were also going for regular evening walks, and people who didn't have dogs were more likely to not go for evening walks. But can we make the same conclusion about the whole population, not about the people who took part in the survey? So that's where the chi-square test comes handy. But for this, we first have to formulate the null hypothesis. And let's say that our null hypothesis of the test is that the two factors, so being a dog owner and going for evening walks, are independent. Then the alternative hypothesis is that those two factors are dependent. And to test the null hypothesis, we first have to compute the chi-square test statistics, which can be computed using the following formula. In this formula, Oj is the observed frequency, which is just the numbers in our table, and Eij is the expected frequency, which is computed using for every cell using the following formula, where Oi dot is the sum of the corresponding line, and O dot j is the sum of the corresponding column, and the values are multiplied and divided by the sample size. So let's pass directly to the example. The expected frequency for the first cell of the table is equal to the sum of the first row times the sum of the first column divided by the sample size, which is 200. E12 is then the sum of the first line times the sum of the second column divided by the sample size. E21 is the sum of the second line times the sum of the second of the first column and divided by n, and E22 is the sum of the second line times the sum of the second column divided by the sample size. Now the test statistics chi-square is a sum where the first element is the value from the first cell of the table minus E11 squared divided by E11, and in the same way we compute the second element from the sum as well as the third element. and the fourth element. And we sum up all those four values and obtain the value of our chi-square test statistics of 25.53. Now, if the null hypothesis holds, this test statistics has to follow a chi-square distribution with one degree of freedom, which is equal to the number of lines minus 1 times the number of columns in the table minus 1, which is equal to 1. And we also have to pick a significance level for our test, and we just pick the most popular value of 0.05. Then the critical value of our test is equal to 3.841, and it can be found in the tables of critical values of the chi-square distribution. So now we have to check if the value of our test statistics, which is 25.53, is larger than the critical value of our test, which is 3.841, and the answer is yes. Therefore, we reject the null hypothesis. Therefore, we can conclude that our factors are dependent, which means that having a dog, the factor of having a dog is dependent on the factor with going for regular evening walks.